For a solving systems video, I thought it'd be a pretty good idea to just sort of summarize a couple days, because it is review, into this practice problem day, where there's a series of problems featuring all sorts of different methods of solving systems, right? It's important to note when I say solve a system, right? If we think about what a system is, right? Like multiple pieces, multiple parts, the implication is that there's two equations, two linear equations. And what's true of two linear equations is either that they do meet at one hyperspecific point, or perhaps they never meet and they're parallel. We do address that it's possible for them to meet constantly, but only if you're kind of cheating, like only if you graph the same line twice over itself, but just sort of write the equation slightly differently. So we're really going to focus on either where do they meet or do they not meet. Right? So to find this where do they meet, it means that the answer to these questions is like a two-part. There's an x, how far over to the left or right do they meet, and a y, how far up or down do they meet. You need to give me an answer that's a point, right? It's a place. Your answer is a place, okay? So if we look at a question like this, where all I'm asking you to do is graph them, it just literally means that can you graph them and can you circle the location of intersection? So if I look at this first equation here, y equals x minus 4, so y-intercept of negative 4, and a slope of 1, up 1 over 1. And what's cool about linear equations is that 2 points is all I ever really need to do that straight line. Now let's change my color and let's work on the next one. Negative 2x plus 2. Okay, so y-intercept of positive 2 and a slope of negative 2. So down 2 over 1, down 2 over 1. It appears that this location right here is the point of intersection. This point 2, negative 2. If you ever want to check your work in these problems, this point should satisfy both equations. It works for both. That's why it's the answer, because when this x and y get plugged into either one of these, it should work. So, is negative 2 equal to 2 minus 4? Yes, that works. Is negative 2 equal to negative 2 times 2 plus 2? It's a lot of 2's. The answer is yes. Okay, so now we've put together a good example for how to solve by graphing. Now let's move forward to other types of problems that we have to solve, like can you solve through elimination? So what do I mean by elimination? What I mean by elimination is it's very difficult to solve for two variables at the same time. But if you can find an effective way to eliminate one of them, you're in good shape. So looking here, is there any way that I could eliminate something right now? No, but I bet that if I multiply this bottom equation by negative 2, that then I'll have a negative 8y and the y's will cancel. Right? Hopefully we remember doing this stuff in Algebra 1. So what does this look like now? Well, my top equation hasn't changed at all. X plus 16y minus 27. Or sorry, equals negative 27. Right? And then we have negative 8x, because I've now doubled it. Or sorry, not just doubled, multiplied by negative 2. Minus 8y. Sorry, minus 16y. Right? Because I'm doubling it. And lastly, let's make sure I get this one right. Positive 4 times negative 2 is negative 8. So let's stack these and put the pieces together. So negative 8x and positive x becomes negative 7x. My y's cancel out. This is the whole point of eliminating a variable, because it's way easier just to solve for one at a time. Negative 27, negative 8, that's negative 35. And if I divide these two by -7, I'll get 5. And that's great, but I'm not done, because remember, it's a location. So x is 5 is helpful to me insofar as I can now plug that value in. I can plug that value in to figure out the rest. So why don't I plug it into this first one here so I don't have to multiply it, right? As in, I can just do 5 plus 16y equals -27, and subtract 5 from both sides. Subtract 5 from both sides, right? When I do that, I get 16y equals -32. And when I divide both sides by +16, I'll get -2. I'm going to encourage you guys not to write your answer like this, but instead to write your answer as a coordinate point. Meaning, can you write your answer like this? That. So let's move on to the next method of solving, which is substitution. And it's very much elimination's cousin. You have a similar goal, which is, can you eliminate a variable, but through a different method, right? When we look at this problem, instead of trying to eliminate something, because I'd have to do some pretty crazy multiplication, it doesn't really jump out to me that there's an easy solution that way. What I could do instead is add 3x to both sides of this equation. Because if I do this, I'll now have a variable that is not eliminated, but it is isolated. Because I'll now have that one singular y is worth, in terms of x, 3x's plus 6. That's useful information to me. If we consider it almost like an exchange rate, I could now say if that's what 1y is worth, then why don't I substitute it for this y, because now the equation will be entirely full of x's, right? So to do that, I now would have -4x. And this is where it gets tricky, because you're substituting all of this in here. So -6, the -6 that I'm looking at, needs to be multiplied by every piece that's in here. So -6 times 3x becomes -18x. And then -6 times +6 is -36. And I can set all of that equal to -14. So why don't I combine my like terms here? -22x. This is going to work out pretty nicely, because when I add 36 to both sides, the difference between these numbers is 22. So if that's really the case, then what is the x worth? Right? What is the x worth? -1. And now I can take that piece of information that I've isolated and substitute that back in. Substitute that back into this right here. What's -3 times -1? +3 plus y equals 6. If that's true, y must be 3. So the coordinate point where these meet, according to this problem, is -1, 3. Now if I want to check my work, I can always return to this right here. And I can always return to that right there. What's -1 times -4? +4. What's -6 times 3? -18. And what is 4 minus 18? It's -14. Now we need to talk about word problems, which for some of you is a nightmare situation. You don't like word problems, and I get that. But really, you just need to be on the lookout for the crucial information in these problems. Just be on the lookout for the crucial information in these problems. Okay? So, do I care what Scott's name is? No, really, I don't. Right? What I'm interested in is, let's see, ticket sales 11, senior citizen, 2 student tickets, costs a total of $171. On the second day, $197 was the total for 13 senior citizen tickets and 2 student tickets. So let's find the price of a senior citizen ticket and a student ticket. So what I can set up here based on the information I was given is that it was 11. We'll call the senior citizen ticket O for old people. Okay, 11O plus 2, we'll do S for student. I can't do S for both, for senior citizen and student, is equal to $171. And then 13 elderly tickets and the same number of student tickets costs $197. Now this is interesting because I'm not telling you to solve by substitution or elimination, but hopefully your critical thinking skills are screaming at you right now that, oh, this is useful to me. I can just eliminate. Why don't I make sure that I'm subtracting everybody and I can solve, right? Subtracting everybody here. So that's -2 senior citizen tickets is equal to, what's the gap here? -26. I'll divide both sides by -2, it'll turn back into being positive. And what that tells me is that a senior citizen ticket, I'll change it to SC, costs $13. And now I need to find out the cost of the student ticket, and I can do that by plugging it back in, right, to either one of these, right? So if I look at the top equation, 11 tickets at $13 each is $143. So $143 plus 2 student tickets equals that day's total. $171. So I'll subtract 143 from both sides and then divide by 2. All right, so what's the difference between 171 and 143? It's 28. Divide both sides by 2. And the student ticket is $14. So nice little dollar discount for the senior citizens. Apparently that's the best they could do. Right? You don't have to worry about writing these as a coordinate point because there's more context here. Right? There's context to the problem. All right, I'll end this video here, but I'm going to do a separate video on a different type of word problem that I think is pretty challenging. But I thought this is a good summary of what it means to solve systems of equations.